Okay, so it goes very fast that we have gone to the number 5 of the machine learning algorithm. And this one is linear regression. And particularly this hour, we only do that by the package, and you will see that it is quite powerful to transform the feature to the answer. So before we start everything, I want to recap what we have learned before and connect to what we are going to learn today. So it is about the supervised learning and unsupervised learning. So let's say we have a collection of data, and we usually write it as a matrix, right? And X is a collection of data. Somehow it does not contain the answer. So for example, you can imagine that this is the feature of a picture, and the answer can be either a dog or a cat, and somehow this one does not provide the answer. So unsupervised learning is try to make a prediction, saying, okay, here is one group, here is another group, and try to label the data by some unsupervised learning algorithm. So this kind of training is called unsupervised. And there are some examples, which is PCA and MDS, K-means, and DB-scan. And all these things are unsupervised. So the key is that it does not supply the answer, but in the end, you have to make a prediction. And our first 4 weeks are spending time to work on this unsupervised algorithm. It is a bit easier because at the beginning you don't have to supply the answer, right? So in terms of the learning curve or the algorithm, how to use that, it is easier to learn PCA. It is just changing X to a new X, and the K-means is changing X to some labels, 0, 1, 2. And that's what we have learned for the previous 4 weeks. So starting from today, we are going to work on the supervised learning. So the only difference is, except for the data X, we have to provide the real answer. Okay, and this time we have the answer. And with the training algorithm, we are trying to make some prediction. We are trying to learn some behavior between the connection between the connection of X and Y, right? And of course, we are not going to see the Y all the time. So based on the X, we can still make our own prediction. And oftenly, we will do something more, right? Because this philosophy is a bit weird. You just told me what is the question and what is the answer, and now I have to predict the answer. And the answer should be just exactly like this, right? So in this case, we have to partition the data into 2 sets. One is the training data, and the other is the testing data. So for testing data, we will supply another set of data. That's called an X hat. And this is another set of data, and this time, after the training and without the answer, the learning algorithm is able to make the prediction. Okay, so the major difference is that for unsupervised, we did not supply the answers. For supervised, we supply the answers. And most of the time, we have to cut the data into two parts. The first part is only for the training. It's like I give you the questions and the answer, and please study hard. And in the end, I hope you to learn how to make the answer. But this is not so hard because the machine just knows the real answer, right? The easiest algorithm is just copy the answer to this place, and you will make 100% of the prediction. So usually we will make another test, and this test is not so different, not so close to the original data. It is similar, but it is not the same. And based on the new question set, and we want the algorithm to learn how to generate the prediction, how to generate the answer. So that's the philosophy of supervised learning. And we will see this behavior in the linear regression. Okay, so that's the big picture, and we are going to dive into the algorithm itself. And if you have a further question, please feel free to stop me at any time. Okay? Now, let's talk about the linear regression. The reason I say it is the linear regression is because that's the picture that we see in the high school or even in most of the statistics course. Okay, I believe you have seen this picture. So let's say we have some points. Maybe you are making an experiment, physics experiment, or doing a survey, and you are trying to build a connection between, say, the mass and the acceleration, or build a connection between the height of a person and its math score, which does not make sense. But this is kind of talking about the relation between two behaviors. And most of the time, they are not going to fall on one straight line. So the picture that you have seen is probably something like this. You will see a line passing through some of that, and it looks like following the behavior of the points, but somehow it cannot pass through all the points because the points are not collinear. And this is what we have done for linear regression. Right? And meanwhile, we call these data points as xi and yi. So what happens is the question usually supply some data from x by data I just mean some numbers, right? And it also tells you the corresponding y. Now, there are different ways to look at this line. This line, usually we learn that as y is equal to a number plus another number times x. And probably the teacher will tell you that, okay, C0 is when x is equal to 0. So the height on this place is called C0. And it has a fancy name called intercept. In our high school, we call that 截距. Okay. But it's just a name, right? It's talking about the distance between this line to the x-axis. On the other hand, this line has a direction, right? And this direction is governed by C1. If C1 is high, then this line is going to be steep. If C1 is equal to 0, then this line is going to be horizontal. And so this C1 also has a name for that. It's called a slope. But anyway, I want to provide you a different point of view on this picture. So from the point of view of data science or machine learning, all we know is about the data and its label, right? So X is the data, and Y is the label or the answer. So basically, we are trying to use the data to make a prediction of Y. And here is how we are going to do that. So one thing we can do is try to find some scalar, C1, such that after multiplying C1 to all these X, then it will be closer to Y. And the other thing we can do is add a constant, C0. Right? So we use the formula C0 plus C1 times X, C0 plus C1 times X, and we hope this quantity is very close to the answer that we want. And that's the philosophy. The goal is try to find out C0 and the C1 so that these two vectors are very close to each other. So for linear regression, we are looking for C0 and C1 so that kind of a C0 plus C1 times this vector is very close to Y. Or formally, you can say the algorithm or linear regressions want to minimize the following quantity, the difference between these two vectors. And I believe this is also how you learn linear regression, I guess. But somehow, maybe in the high school, the teacher only asks you to remember a formula for C0 and also a formula for C1 and try to just do some exam. And we're going to learn some more philosophy behind that and theory behind the scene. Okay, so I believe this part is quite close to what you have learned. Now we want to talk about a general case about linear regression, and it will help you to understand the algorithm that we are doing. So here is the general case. Okay, so if you recall what we have done previously, we usually have a data which is an array, and this array is n by d. It has n samples and d features. And because we have mentioned that it is supervised learning, then we also have the correct answer. And you can imagine that this is a simple one and some features. For example, this is student number 1, and this is the score of math, score of physics, score of English, and then you want to make a prediction of maybe he or her future outcome or highest degree, that kind of thing, or just a different score. So we are trying to make a connection between X and Y. And now what we are going to do is quite similar to the previous slide. Instead of looking at X by row, this time we are going to look at X by its columns. So, as mentioned before, you can imagine that, okay, this column, it is the score of mathematics, the score of physics. So each column represents a feature. And so now we are trying to find out C0, C1, C2, and CD, so that C1 times the first feature, C2 times the second feature, and the weighted average of these features plus C0 is pretty close to Y. So the goal this time is try to look for some coefficients C0, C1 up to CD, so that C0 plus C1U1 plus C2U2 plus CDUD is very close to Y. And I want to emphasize that this quantity, you can imagine that C1, C2, and CD, these are the weights. And the higher weights means this feature is more important. And the whole thing here is the weighted average or weighted index. 加权指数哦，跟台湾股票一样。Okay, so if you think this math score is very important, maybe this C1 you will multiply by 5, and this maybe physics you will multiply by 3, and other score has different weight. You assign the weight to each of the feature and make the sum of them, and this come out with a new index. And again, this is called the intercept. Somebody call that as bias, but the thing is that you are going to shift the whole data by by some number. So the whole idea is try to find some weights to each feature and taking the weighted index, and after the shift of intercept, I want this whole thing is very close to our answer. So that's the goal. And the other way to think about this is, you see this is a C0, it's just a number, and somehow this is a vector. You have a number plus a vector, which is not making sense. You can imagine that it is like this. You can do X, and again X has U1 up to UD, but this time you try to add one more column, which is all one's vector on the left. So by doing so, you can say, okay, I want C0 to be here. C0 times 1 is C0, right? So I want C0 to be a constant in the first column. And then I still do C1 up to CD. So what you can do is assign a all ones vector in the front, and so that C0 is just a usual weight in the front. So equivalently, we are looking for this x and try to augment that by a vector 1. And then we are looking for some coefficients. And you see the coefficient put in on the top is the same as the matrix multiplication. We have C0, C1 up to CD. And we want this quantity to be very close to y vector. And how to measure the closeness of two vectors? We can do the norm. We just calculate the distance between these two vectors, and we want it to be minimized. Can someone help with the aircon? The remote is here. If you feel hot, you can just do that. Okay, so that's really the theory behind the scene, or the philosophy about the linear regression. We're looking for some weight, and so that the feature is weighted, and then do some intercept, and it will very close to the outcome. So sometimes these weights are also called coefficients. Okay. Any questions here? We are almost there, and I will show you an example very soon. Okay, so let me finish the syntax and the parameters, and we should be ready to give you some example. So we are not going to do the calculation by hand because we are in the classroom and we are learning the machine learning. So we will do most of the thing by the coding. And the syntax is as follows, and it is pretty much the same. We have to do from something to import the package. This one is in the linear model. The name is super long, but remember you can press tab to to do the autocomplete. And then you can say model is equal to this linear regression. You can supply some parameters. After that, you do the fit, which is the training part. So when you are doing the training, you have to supply the data X, and you have to supply the answer Y. And this is the kind of the training data. You supply the first set of data and first set of label and try to train the model. After the model is trained, you can do model.predict. And this time you can supply X test. By doing so, the function will output the prediction. We call that as Y new. So the last step here is the prediction. So it should be easy enough, just as what we have done before, but this time you are supplying the data and the answer at the same time. And just making the prediction, you have to supply a different set of data, which is making sense. Now, the parameter is also easy. Okay, I would say maybe this is the only important parameter for this algorithm, which is fit intercept. It is either true or false. If true, then it is going to train C0. Otherwise, it is not going to train C0. It will assume that C0 is equal to 0 and just ignore this parameter. So as you can see, it's like C0 plus C1 U1 plus C D UD. I want it to be very close to Y. This is for the case of fit intercept. And you can imagine that in the previous case, we are doing Y is equal to C0 plus C1x. And if C0 is equal to 0, then we are just only training C1U1 plus to CDUD, and we wish that to be very close to Y. And so in the previous case, we are trying to train Y is equal to C1x. So you can imagine that this is a line that passed through the origin, and somehow the second case is rarely used. Okay, finally, I have some attribute to say, and then we'll show you the code. You can call the attribute by model.something, model.coefficients. You can output the array, which is all the coefficients, C1 up to CD, not including C0. And this is because C0 is stored in intercept.